Right, first up, let's have a quick look at the things that you are supposed to know from the previous lesson, 7.3. So we were looking at reaction profile diagrams, and of course they show the relative energies of reactants and products, and also the activation energy. And we talked about this idea of activation energy as being the minimum energy required to start a chemical reaction or to break the bonds. Right, first up, see if you can remember how to draw an exothermic and an endothermic reaction profile. So if you just quickly pause this and have a go. Right, hopefully your exothermic one looked a bit like this. We've got energy on the y-axis, reaction pathway or progress or something like that along the bottom. Reactants align, doesn't matter where, as long as they are above the products. And remember, first of all, the graph goes up because that's the energy required to break the bonds, and that is called the activation energy. And then it comes down, and that's the energy that's being released when the new bonds are formed. And hopefully you might have labelled this difference here as being the energy change, or delta H. Endothermic is kind of the opposite. Remember, the products need to be higher than the reactants, and you've still got the graph going up to break the bonds and then down as the new bonds are formed. This time you've got a positive change though, going from the reactants to the products. Okay, so today's lesson we're going to have a look at the following things. First up, that during a chemical reaction you need to supply energy to break bonds. All right, basically these things are already bonded together, so to break those you have to give a substance energy. And when those bonds have been broken, the atoms are unstable, therefore they will come together and energy will be released when those new bonds are formed. This amount of energy released, all right, can be calculated from something called bond energies, which we will look at shortly. And the difference between these different energies to break and to form the new bonds will give you the overall energy change. Again, that will become obvious later on in the lesson. And in an exothermic reaction, the energy released from forming new bonds is greater than the energy needed to break existing bonds. Again, we'll talk about that shortly. And this last one is the exact opposite. So if you look at that statement, it says this time the energy needed to break the existing bonds is greater than the ones released from new bonds. All right, so these are opposites. Okay, so how do we actually do this? How do we calculate this energy change, or delta H, for an exothermic reaction? Well, if you quickly sketch your reaction profile for an exothermic reaction, give that a go there, exactly like we did just now. So if we look at our exothermic reaction, so this time between nitrogen and hydrogen, you give it some energy, bonds are broken, and you break all those bonds and get your nitrogen atoms and your hydrogen atoms, and then they come together and form your product, which is 2 molecules of this NH3, which you might recognize as being something called ammonia. Okay, so the energy change, so that's the difference between the reactants and the products, right, can be calculated using, well, to be honest, you can probably have a look at that diagram and work out the actual, you might be able to work out the calculations. Have a little look at that. But formally, it's given as follows. It is the total energy to break the bonds, so that's this value. Take away the total energy released when the new bonds are formed, so that's this value. You will notice that in this case, because exothermic, that is a larger number. So what that means is you put those numbers in, 2253, there it is, 2346, there that is, take one away from the other, and you will get minus 93. These units hopefully you recognize as being kilojoules, so that's a unit of energy. Right, it's negative because the energy has gone down. In actual fact, because they've asked the energy change, they don't really mind if you leave that off, right? Because the change is 93. Obviously, it's gone 93 in a negative direction, right? But 93 kilojoules would be the answer to that question. Incidentally, I haven't got an example for an endothermic one, but the method would be exactly the same, right? So it would still be the energy to break the bonds, take away the energy to form new bonds. And endothermic, of course, the products would be higher. So you should know if you've got this right or wrong, because in an exothermic reaction, it will always be negative. And in an endothermic reaction, it will always be positive. Which leads us to this statement. In an exothermic reaction, it's exothermic. By the way, this is a very common exam question. They will often ask, why does the diagram, or why does your calculation show that a reaction is exothermic? So it's exothermic as the energy required to break the bonds, as in this value, is less than the energy released forming new bonds, as in that value. Have a think about what that sentence would look like if you were describing why something was endothermic. So if it was endothermic, you would be writing the energy, it's endothermic as the energy required to break the bonds is greater than the energy released forming new bonds. So it's the exact opposite. Right, so that previous slide was a kind of simplest way that you might get asked this. However, it's much more likely, particularly in the higher tier, that you will be asked to actually work out the total energy required to break the bonds and the total energy released forming new bonds. And to do that, you would have to be given data like this. You would always be provided with this. You'll never have to remember these numbers. And this is literally the bond energy in kilojoules per mole. So the number of kilojoules released for every mole of that particular bond. All right, and you can see you've got carbon, 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 oxygen, all of these different things. You would need to use these to actually calculate the total energy from the bonds being broken and the total energy from the bonds being formed, and we'll have a look at how to do that. Okay, the easiest way to look at how to do bond energy calculations is to actually do some. So you might be given a question like this. So methane reacts with chlorine. This thing is methane, CH4. This is chlorine, Cl2. And it forms this substance, which is something called chloromethane and hydrogen chloride. Some bond dissociation energies are given in the table, right? That word might scare you a little bit, but dissociation means breaking, right? If you've got, yeah, you might have some knowledge of that. It doesn't really matter. They may use that word, they may not. All right, are given in the table. So here's the different bonds: carbon, hydrogen, carbon, chlorine, 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 hydrogen, chlorine. And this is the energy required to dissociate or break those different bonds. And the question would be, calculate the energy released in this reaction. Okay, so how do we do it? Right. Total bonds broken. So the total energy required to break the bonds, take away total energy required to form the bonds, will give you your change. Now, if you were doing this actually on an exam paper, this way around, so this bit is this side, so that's the reactants. Total bonds formed is this side, so the right-hand side, that's the products. Right, so it's literally a counting activity, which seems relatively straightforward, but do be careful. It's very, very easy to make a mistake on this. So if you have a look at your reactants, you have got 1, 2, 3, 4 CH bonds and 1 Cl bond. So it would be 4 lots of 413, 1 lot of 243. If you look at the products, you've got 1, 2, 3 CH bonds, 1 CCl bond, 1 HCl bond. So it'll be 3 times 413, 327, 432. So there's that as a sum. So where's that come from? So 413 times 4, there are 4 CH bonds. Add the CL-Cl bond. Take away 413 times 3, that is because there are 3 CH bonds. Add the 327, that's CCl. Add 432, that's HCl. Right, be very careful with your calculators here. Notice you need brackets, so it's very easy to type in 413 times 3 and then not put your brackets in, so make sure you do that, otherwise you'll get into a mess. I would also say make sure you calculate the bonds broken and the bonds formed separately. Don't just tap it all into one massive sum. and write down the total to break it and the total when they're formed, because you will often get a mark for those. So in this case, it should be 1895, take away 1998, and of course, if you tap that in, that will give you minus 103, and the units are kilojoules per mole, because it tells you that in the table. Little reminder, it's negative. Why? Well, because it's an exothermic reaction. How do I know it's an exothermic reaction? Because the energy required to break the bonds is less than the energy required to form the new bonds. Okay, so another example. This one's a little bit more complicated, but not too bad. So you've been given this particular reaction. You've got this stuff, methane again. This time they're reacting with oxygen. So by the way, that's a oxygen double bond, hence there's 2 lines. To form this stuff here, it's something called methanol. You need to know that at the moment. Right, just notice though, they've balanced it. So there is a 2 here and there is a 2 here. That 2, when you balance equations, means 2 lots of this whole thing. So 2 lots of the CH4, and this 2 means 2 lots of the whole thing. So this whole methanol molecule. And that is going to be important when we do our maths. So once again, it's the total bonds broken. So the total energy to break all of those reactant molecules. Take away total bonds formed, that's the total energy to break, total energy released, forming the 2 methanol molecules. Right, this time, see if you can actually have a go at calculating the total energy required to break the bonds and the total energy released forming new bonds using this data over here. Give this video a pause and have a go. Okay, so first of all, total energy required to break all the bonds. Now, this is the issue. There are 2 molecules of CH4. So you've got 1, 2, 3, 4 CH bonds times 2. So there are 8 lots of 435. Then there is 1 oxygen double bond, which is 497. So that should give you 3977 kilojoules for your total bonds broken. So total for the products, again, you've got the 2 molecules of this stuff, CH3OH, so 2 of these. Right, you've got to double everything. So there are 1, 2, 3 CH bonds times 2 gives 6 times 435. There's a CO bond, but because there's 2 of these things, it's 2 times 336. And there's an OH bond, and because there's 2 of these, it's 2 times 464. Add that all up, and you will get 4210. Then let's just quickly plug those 2 things in. So reactants take away products to give you your energy change, which is minus 233 kilojoules. Once again, that tells you this is an exothermic reaction. In case you didn't know, exothermic reactions are much more common than endo. So it's an exothermic reaction. Why is it an exothermic reaction? Because the energy required to break the bonds is less than the energy released forming new bonds. Okay, so before you have a go at the examples yourselves, the exam questions, let's have a quick run through everything. So I think you probably knew this already, but just a reminder that energy is obviously supplied to break bonds, energy is released when new bonds are formed. You've got to use bond energies to be able to calculate those things. To work out the energy change, you look at the difference in the sum of the energy, so the total of the energy needed to break the bonds and the total of the energy released when bonds are formed. And remember, exothermic reaction, the energy released forming new bonds is greater than the energy needed to break existing bonds. When I've been saying this, At exothermic reaction, the energy needed to break the bonds is less than the energy released forming new bonds. Hopefully you can appreciate that. It's exactly the same thing. And then the endothermic reaction is the opposite. Just as a little tip before you have a go at the exam questions, do be very, very careful counting your bonds. That's the most common thing that people do wrong, other than bad use of calculator. That is also common. Some of them will require you to rearrange some bits and pieces. All right, so for example, rather than getting you to calculate the energy change, they might ask you to calculate the energy of a bond, which is a bit trickier, but it's essentially just the same thing with a bit of a rearrangement.